All right, welcome everybody. My name is Frank Seide. I'm a principal researcher in the speech group in Microsoft Research, and I'm also the architect of CNTK, which is what I'm going to talk about now. So how many of you have attended Satya Nadella's keynote yesterday? Okay, so the theme of that keynote was democratizing AI, and Satya talked about how we're making the deep neural networks that we're using in our own products available as cognitive services, for example, for image captioning and speech recognition. And he also showed how we're putting FPGAs into the data center to make these models faster and cheaper to evaluate. What CNTK is about is democratizing the tool chain. So CNTK allows you to build your own deep neural networks in the same way that the Microsoft product groups do that. So in a nutshell, CNTK stands for the Microsoft Cognition Toolkit. It's an open source deep learning toolkit that is very easy to use, or it's designed to be easy to use. So we try to get you focused on what, not how you're doing things. It's fast, it's very flexible. It has first-class support for Windows and Linux. And one thing that's kind of cool about it is there is no separate internal version. So everything that the product groups use is actually out there on GitHub in the open. So deep learning has really changed the way that we do machine learning for these cognition tasks like speech recognition, machine translation, image classification. And a lot of Microsoft product groups and Microsoft products basically got sort of, how to say that, infected by deep learning models, including the cognitive services, Skype Translator, Cortana, Bing, HoloLens. In Microsoft Research, we're doing a lot of that. And there's a lot of groups that I don't even know about. So you probably all know how important and how profound the change from deep learning was. But I just still want to give you two examples. So the first is the ImageNet task, which is about classifying images. And does this work? Huh? Yeah, OK. Can you see the laser? It's very weak. OK, so let me see. Can you give me a stronger laser pointer by any chance? OK, so you see all the way on the left, in 2010, the error rate on this task was about 28.2%. And then through the introduction of deep learning, we brought it down to 3.5%. And this was specifically through a technique called residual learning that was invented by my colleagues in Microsoft Research in Asia. That's nearly an order of magnitude of error reduction. And you can do fun services with that. For example, a caption bot that describes what it sees on a photo, or stuff a system that tries to guess the age of people in a photo, but also more serious things like Satya Nadella talked about yesterday, the service that Uber is using for face verification of drivers. So another area where deep learning was really, really important was speech recognition. So on this task, you see how the error rate on various speech recognition tasks has come down over time. Oh, yeah, thank you. Where's the button?
Yeah, I would just leave it on.
It's on. OK.
It's not doing it.
Yeah, it's working. OK, good. So the curve that's particularly interesting for me is this curve here. This is the switchboard task, which is about transcribing people talking on the phone to each other. And this has been long sponsored by the US government, research in this area. So it's not the point here why they're doing this. You can think about that by yourself. But you see, at that point, it plateaued for quite a while. And people kind of even lost interest. And we were hanging at an error rate of about 24%. And then in 2011 and 2012, my colleague, Dong Yu, and myself showed that by introducing deep learning, you can actually cut that error rate by 42%. So we brought it down to 14%. And just to give you an idea on what speech transcription looks like at that error rate. So this is a demo that we gave in 2012, transcribing our then corporate vice president of research live on stage. We were closed captioning him, and that model was actually not specifically trained to his voice. Oops. Can we have audio, please?
Statistical techniques
and
big data have allowed us to do a much better job than we previously were able to do in being able to translate web pages or other kinds of information into other languages.
So it's very, very readable. And once you have an accuracy level like that, you can even do cool stuff on top of that, for example, combining it with a translation system.
But this technology is very promising.
用这个技术很有希望。
And we hope in a few years that we'll be able to break down the language barriers between people.
数年后，我们希望能够打破人们之间的语言障碍。
Personally, I believe this is going to lead to a better world.
这我个人认为，这将导致更好的世界。
I hope you enjoy the rest of the presentations today.
Okay, so he said this will break down the language barrier, and it turns out it already has done. This was the earliest public demonstration of what has become Skype Translator. And if you have the latest Skype desktop client on your PC, you will actually have this functionality built in. You can now make translated phone calls with it. And one thing that I'm particularly happy about is just recently we announced that we were able to cut that error rate way further, all the way down to 6.2%. And Satya Nadella yesterday said 6.3, so 6.2 is actually the latest number. And all of these experiments were run with CNTK. We're getting damn close to, the accuracies that humans are actually achieving on the similar task. Okay, so what I want to do today is I want to first explain to you, well, what is CNTK, then how to use it, basically to give an idea on how would it fit like into your workflow, what would it look like to use it. I'm going to do a deep dive into some of the technologies that make it special, and I'm going to go through a number of examples just to give an idea what the source code looks like. So, well, what is CNTK? It stands for the Cognition Toolkit. CNTK is Microsoft's open source, cross-platform toolkit for learning and evaluating deep neural networks. It expresses nearly arbitrary neural networks by composing simple building blocks into complex computational networks. And CNTK is production ready. So I will go through these points in more detail. So first, CNTK is actually developed in an open source model, and we're using the same model inside and outside the company. It was first created by my colleague in 2012, and then open sourced about 1.5 years ago. First to Coldplex, and since the beginning of this year, it's been on GitHub under a permissive license. And what's really cool about it is that we're all sort of working out loud. So all the development that's happening is happening in that public GitHub repository. You can see my commit from last Friday. You probably don't want to see it because it's not really working, but you can see that if you know which branch it is. And this is also used by more and more Microsoft product groups now. So many CNTK-trained models are powering products from Microsoft right now. And we even have sort of full-time contributors from other teams that feed into CNTK. We have external contributors from MIT and Stanford, and CNTK runs on Linux, Windows, Docker, it supports Qt and 5. And in about a month from now, we will have a beta version where you can use Python and C++ directly to access it, followed by .NET as a next step. So I want to talk about the most important thing is the concept of computational networks. So what's a computational network? For that, let's walk through an example. So I hope the laser pointer works enough. You can see this So this is sort of the simplest deep neural network. It's deep because it has 2 hidden layers. So see what happens. The input is, no, this is not working. So look at the first formula. The x is the input. And the x gets projected by multiplying it with a matrix. And you add a bias. And then you run it through some nonlinearity. For example, the sigmoid function. And that is the output of your first hidden layer. Then you repeat the same structure for the second layer. And what comes out there is your second hidden layer. And then again, you project that and add a bias, but you run it through a different nonlinearity, which is softmax. And this gives you a probability that a certain input belongs to a certain certain class. And if you want to train this model, you also need a ground truth. And you need to write down a criterion, very often the cross-entropy criterion, that basically maximizes the probabilities for the correct class. And what the task of training is to adjust these weight matrices and the biases to maximize this objective and give you the best classification. basically. So in CNTK, if you want to do this in CNTK, the first thing you need to do is translate it into the way that we are writing formulas. So this is very straightforward. And then what CNTK does with this is it turns it into a computational network. So you see in this network, each of those little circles there, the nodes, are operations. They're primitive operations. And the network also has inputs. There's X is the data input, Y is the ground truth, and then you see the weight parameters on the left. And so the values that flow through that network are what we call tensors. They're n-dimensional arrays, and they can also be sparse. That's very important for language processing tasks. So what is actually quite cool about having this graph, you can do a lot of interesting things with this. And one is you can automatically compute the gradient. So what do I mean by that? Well, the training works roughly like this. You run a training sample through the network, and then you look how well are you doing. And then you sort of kick a little bit against the system so that next time you run the same sample, you would be doing a little bit better than the last time. And what does it mean to kick a little bit against the system is you have to compute the gradient with respect to your objective function, and then add the gradient weighted with a small weight. And the thing that this graph gives you is that you can automatically compute the gradient as long as you know the individual gradients of these little nodes. So for example, if you want to compute the gradient with respect to, of the CE criterion with respect to B1 on the lower left, this is just a product of the gradient with respect to P times the gradient of P with respect to the input of the softmax function, and so on. So you just multiply everything that's on the path down the way to the variable, right? And that's really nice. You don't need to worry about that at all. Another thing that's really nice is that we can optimize, for example, for memory. So imagine you are doing inference. You really only need 2 buffers, right? You need an input and the output of the node. Once you have consumed the input, that memory can be reused for the next node, and so on and so on. So you really only need 2 buffers. In training, you need a little bit more. For some of those nodes, you actually need to keep some of the values around because they're needed for the gradient computation. And because CNTK has this full view on the graph, it can optimize that for you, and it can decide which memory buffers it can reuse. Also, once you have a graph, you can do things like clone it and modify it and so on. OK, so this is the most important concept that we have in CNTK. And what this gives you is this sort of Lego-like composability, right? And this allows us to support a wide range of things, such as feed-forward DNNs, recurrence, convolution, DSSM, sequence-to-sequence, for all the important tasks that we're working on today. So the third point was CNTK is production ready. It gives us state-of-the-art accuracy on benchmarks. So for example, we used it to build the world's best speech recognition system. But also very important is that we have first-class support for multi-GPU and multi-server parallelization. And that's really, really important. Most of the other tools don't give you that. And I believe TensorFlow gives it to you, but people tell me that it's actually really hard to set up. And CNTK makes it really easy. So for example, here's some benchmarking that a university in Hong Kong did. I wish I could point. So the left column, FCN8, this is a fully connected network. We're beating the other 4. On the right-hand side, on LSTM, we're faster. This is runtime. We're faster than everybody else. In the other 2, we're in the same ballpark. And one thing is interesting is TensorFlow is never faster as CNTK. And what's also interesting is if you compare the parallelization. So for example, the blue bar here compares single GPU performance. And this was done in December 2015. So Theano and TensorFlow have caught up a little bit. So they're pretty much all on par here. And then you see the orange bar where we go to 4 GPUs. CNTK nearly scales 4 times. And then we go to 2 times 4 GPUs. That's 2 machines. The other toolkits did not support that at that time. And now it's only TensorFlow that does. And it still scales quite nicely. OK, so how would you use CNTK? Let's take the most important task, which is training neural networks. In order to train, you need to configure how you read your data, what your network looks like, and what the learner parameters are. The learner is SGD in this case. Once you have that, you can take a corpus and train a model. So how does that look like? Well, CNTK is a command line tool. So you run that by giving it a configuration file. See on the command line. You can also give it a couple of other additional variables, such as command and root. And command is a special variable. What it will do is it will look at the items that you list there in the config file and look for respective configuration blocks. So here's an example of the myTrain block. And it defines a couple of variables. It says it's a train block. The device ID should be selected automatically, so it picks the next free GPU. And it says where the model should be saved. And then you see these three blocks, the reader, the network, and the learner. And those are, again, configuration blocks. So let me talk about the reader. Reading, turns out, is actually a very non-trivial task. Why is that? Because in SGD, you need to produce or present your data in a randomized fashion. And that's easy if you can load everything into RAM. But for example, in speech, RAM was always a little bit too small for the data sets that we worked on. When I had a 4 gigabytes machine, we had 20 gigabytes. When I had my 64 gigabyte machine, it was 90. When I had 128, it was 200, right? So the way that we're doing this is we're basically chopping the data into blocks and randomize the blocks and only keep a subset of the blocks in memory and then pull samples from there. And that is actually a very, very efficient algorithm, and that's something that would be actually, it's quite tricky to implement that if you want to do this by yourself in Python. So to get your data into CNTK, well, if you have standard formats such as images or some of the standard speech formats, we have standard readers for that. The other option is you can convert your data, for example, into the CNTK text format. This is an example to create an English to French translation corpus. And very soon, we will have a Python interface, so you will be able to implement a custom deserializer in Python that will still benefit from all this blocking and everything that I talked about. And if you have small data, of course, if you're running in the Python environment, you can just load it into RAM. OK, so the next question is, how do you define your network? The network specification consists of the network formula. So you saw some formulas in the beginning. That's an example. You have to declare what the inputs are and what the outputs are and the evaluation and training criteria. And so with these network descriptions, we call them brain scripts because they're sort of the scripts that our little brains operate according to, right? And we actually have a custom description language. We call it brain script. But if you don't like that, very soon you can also use Python and C++, and then also C# and .NET. So what does that look like? You already saw a bit of brain script here. So you need to do a little bit more. So let's define a couple of dimensions here. You need to declare what your inputs are. And now you need to start defining your parameters. Now, this is the first layer, second, and third. And now that can actually become quite tedious if you want to do this for this residual network that I talked about in the beginning, which has 152 layers. So this is sort of the most basic, low-level way of describing things. So now you can actually define functions to create reusable blocks. This actually, I think, is very straightforward, right? It takes 3 arguments, x, the dimension for output, the dimension for input, and an activation. And you can just use this by invoking the function. Now, still, this is not very convenient for 152 layers. So the next thing you can do is you can use recursion to automatically create entire stacks of networks. So here you pass an additional parameter, capital L. If that one is 1, it just invokes the layer function. If it's more than 1, it invokes itself with a L-1. So it basically creates a stack that's 1 layer less and then puts another layer on top of that. And now you can invoke this with basically with a parameter. So this makes it very easy to optimize over varying numbers of layers, for example. So we can go a bit further than that. So if you're familiar with Keras, probably some of you have seen that, you probably are more familiar with a pattern like this, where you're creating layers and then applying them. You can do the same thing in CNTK by actually creating a function that returns another function. So what you see here, this one defines W and B as the parameters, but then it doesn't return the value, but instead another function that you can then apply to your data. And so once you have this format, you can actually go one step further. For example, you can compose models through this sequential expression. This is a lot of the other toolkits have something very similar to this. And so now you see how we're getting more and more abstract in the way that we're describing, and you're really focusing more on what you want to describe and less so on how you're actually describing it. And this is a very direct representation of the network there on the left. Actually, this activation equals sigmoid is kind of silly. You can also write it like this. OK, so you got a rough idea. And just to give an idea, there are a number of predefined layers, dense layer convolution, max pooling, recurrence, and so on. So all the important things are there. And what is not there, you can write it yourself in many cases using the lower layers of BrainScript. So BrainScript is a direct, down-to-earth, easily understandable syntax that has this high-level composability, and it has this powerful yet easy-to-use standard library. And again, soon you can use Python and .NET and C++ for that. So why BrainScript? Where does the name come from? Well, the full name sort of expresses our grand ambition, right, of building a brain. But the two-letter acronym sort of expresses where we are today with respect to that great vision. Okay, so last thing, the learner configuration. The only thing that's really important, I mean, you specify the mini-batch size and the learning rates and everything. The important thing is that everything is here at one glance. If you look at some of the other toolkits, sometimes kind of scattered out your code, and here it's all in one place and easy to see. So what does a typical workflow look like? First, you write your configuration, create your data, and then you call CNTK. You can actually combine training and evaluation by invoking multiple blocks. And now probably you want to parallelize. How do you parallelize? It's actually very simple, just MPI exec. And then you define on MPI exec what the machines you want to use, and for CNTK, you just have to tell it parallel train equals true. Then you can do things like modify the model for incremental layer building, and you can apply a model file to file using the command line. And if you want to use the model from code, we have, at the moment, a library, eval-dll, actually has the same name on Linux, don't know why. And in the future, you can use this new API that we're using, that we're creating. Okay, so this gave you, I think, an idea what CNTK is and how the typical use would look like. I now want to dive a little bit deeper into a few technologies that I think make CNTK a little bit special and that are different from the other toolkits. So the specific techniques I want to talk about is how we're handling time, how we're doing mini-batching of variable length sequences, which is, if you have used other toolkits, that's really a kind of a little bit fuzzy and hairy problem, and how the data parallel training actually works. So let's create a recurrent network as an example. So this is the same thing that you saw before. If we want to turn that into a recurrent network, the first thing we need to do is introduce a time dimension. And then we introduce the recurrence. So now you can see that h1 at a given point in time now depends on the value of h1 at one time step before. All right, this is the typical way of writing the formula. In CNTK, you write this slightly differently. We still do not have an explicit notion of time. Instead, you have this sort of magic function here called past value, and that basically says you're accessing the previous time step of the same variable. So what does that look like in the graph? So this is the same thing. So let me modify the graph, make some more space first. And so this is what you have now, right? So the red loops there, this is the recurrence. And so you can actually see one thing very important here, that a large portion of the graph is actually not participating in the recurrence. And why is that important? It's important for efficiency. Because if you're running on a GPU, you really would like to launch your operations in as large CUDA launches as possible. So everything that's black here can be done in a single CUDA launch. And only what's red has to be serialized with multiple CUDA launches. And CNTK basically analyzes this whole graph for you and finds sort of the minimum loops in there, and only those will be launched in individual launches. Everything will automatically be grouped together. And you don't even know that, or you're not aware of that. And just to give an example how important that is, you see the loop, there's one variable, this h1, that hangs off there. In the initial version that we wrote, that was actually included in the unroll loop. So it would actually update the h1 in the training, the gradient, in a frame-by-frame fashion. At some point, I noticed that, hey, we don't need this. We can do this in one big bulk. And it turns out, just by this modification, the training became 15% faster, just with a like 5-line modification optimization in the code. So these things are really important for performance. So as I said, CNTK automatically unrolls those cycles, and that also makes the system very efficient and very composable because you don't have explicit notions of time. It's easier to share and create multiple blocks that you can plug together. If you compare that, for example, with TensorFlow, so there you have to manually unroll the loop. This is from, I just pulled this yesterday from the latest example that's there for recurrence. So you see the for loop there, where you have an explicit for loop over all the steps, all the words, And so basically both the time dimension, also the batch dimension, you see batch size, is basically it's always present in your mind. You always have to think about that, right? And CNTK, you don't even think on that level. It's just giving you a different way of thinking about problems. And so the next question is, how do we deal with sequences that have variable lengths? So in most of the other toolkits, you would typically group sequences of similar lengths together and then do a technique called bucketing. So we do that differently. So we can actually pack sequences of varying length into the same mini batch. So let's start with a long sequence, and then we add one that's much shorter. So we can put this in parallel. So parallel means these two sequences can be executed with parallel CUDA launches. So now we add one more. There's more space. So we can actually concatenate it. So we don't need to open up a next parallel sequence, which is what many other toolkits would do. And that gives us better parallelization. So let's add a couple of more. One more. And then you see at the end we have this padding area. There's a bunch of garbage there, right? And now with this structure, we can, for example, perform a recurrence from left to right by launching the first four sequences there in one step. They can be parallelized. But the next one has to wait until the first one has computed. And then once you reach the end of sequence 2, for example, something special happens, because you need to make sure that you don't accidentally carry over the state from sequence 2 into the beginning of sequence 3. And so CNTK handles that for you. Also, when you compute the gradients, you need to make sure that you don't accidentally pull in data from the padding, for example. On the other hand, when you do non-recurrent operations, like the final softmax, you can just take this structure, flatten it out, and launch it as a single CUDA launch. And yeah, you're computing a little bit of garbage in the padding area, but it's garbage in, garbage out. You know how to ignore it later, and that is much more efficient than doing it in little pieces and trying to avoid to compute this. So CNTK basically does this for you. This is fully transparent to you, and you don't actually need to know how that works or that this even exists. And you get automatically the speed up from this. Next slide. Yeah. Okay, so to recap, the user never really explicitly sees a time or a batch axis. CNTK infers the loops from your network description and is totally transparent. Don't worry about batching and packing and padding. And again, it's like focusing on what you want to do and not how you're going to do it. And no bucketing. So the other technique, the important technique that we have is data parallel training. Now, data parallel training, think about it that way. You get a mini batch, for example, 1024. You have 16 workers. So now you take that mini batch and chop it up into 16 pieces and distribute that over 16 machines. So every machine now computes 64 frames. Once you have computed these 16 partial gradients, you need to bring them together again. You need to accumulate them to compute the full gradient of the mini batch, and you can update your model. So if you try to parallelize that, you will very quickly find out that this is hopeless, because the time that it takes to compute the mini batch without any parallelization is about the same as the time that it takes to do the data exchange. Right? So at best, you can maybe speed it up by a factor of 2 or something like that. So it's really, this is kind of hopeless, right? And that's true for all the algorithms. It's true for ASGD and other toolkits and so on. There is a natural limit on how we can parallelize. So how do we approach this? There's two ways. One is you can try to compress your data. So every time you exchange data, you exchange less data. And the second is, well, you can see, do I actually need to communicate that often? Can I do that less often? And CNTK has sort of solutions for both of that. Let's talk about the first one. So it turns out that we found you can actually quantize gradients. You can quantize them very, very aggressively, down to a single bit. Okay, so that sounds crazy, but the trick is, every time you actually send a quantized gradient, you can know what the receiver will think what this is, and you can compute what the error is of the data that you wanted to transfer, and you remember that error on your own side in a residual accumulator somewhere. And then for the next mini batch, you take that residual and add it on to the mini batch that you want to transfer. And again, transfer it at 1 bit and keep the residual again. And that will give you, for signal processing people amongst you, this is similar to sigma delta coding, or we have seen yesterday these fancy pixelized pictures that we're creating, and this is actually error diffusion. It's a very, very similar technique. And it gives you a factor of 32 better bandwidth And this really brings you into the range where it can very nicely parallelize over like 16, 32 machines or something like that. The next thing you want to do is you want to actually see if you can grow your mini batch in the sense that instead of, say, updating your model every 1024 frames, maybe you can do it every 2000, every 4000. And it turns out in the beginning of the training, you cannot do that. You will have a problem with convergence. But as you go through the training and your learning rate becomes smaller and smaller and the model becomes better and better, you can actually reduce the number of model updates. And it turns out that very quickly it goes up to, say, mini batch size of 3,000, and maybe halfway through the training in our speech example, it goes all the way to 100,000 samples for a mini batch. And at that point, of course, you understand that all this communication bandwidth problem is essentially gone. Well, that's only true up to a certain amount. If you want to scale bigger, then there's another technique. And there the question is, well, what if I do multiple mini batch updates without actually exchanging data? So now let's imagine you have 16 workers that run in parallel, do multiple mini batch updates without talking to each other. And then you maybe do 500 mini batch updates. So at the end of that, you got 16 partial, increments from a common starting model to 16 different final models. You can call that a block gradient. It's like the difference, how you got from here to there. Now you aggregate this block gradient across the 16 machines. You get this really big monster gradient. And if you then add that gradient to your model, you will immediately diverge. That's not going to work. We wish that this would work, but it doesn't. However, there's another technique called model averaging, where we know that if you don't add this gradient in its full force, but maybe if you have 16 workers, you add only 1/16 of it, then you're actually staying in a nice range. It doesn't diverge or anything. But that's a bad idea because now you're converging basically 16 times slower because now you're weighing down every gradient by a factor of 16. So the idea of block momentum is now to use the error residual again. After every block, you only add 1/16, but you remember that you still have to add 15/16 in a residual. When the next block comes along, you take that error residual and add it on, and again, of that you only add 1/16 and keep the rest in an error residual. So that spreads out the gradient application quite a bit, but it doesn't weigh it down. Every gradient now counts still, every single sample now counts the same as before. And it turns out that method actually works really, really nicely. And if you write down the formula, then you will find it looks like the momentum formula. So we call this block momentum. So this chart here shows what kind of parallelization efficiency you can get. If you maybe look at the middle part, 16 GPUs, the orange bar is this 1-bit technique, and the yellow bar is the block momentum technique. And you see the block momentum here scales to what's at 14 with 16 GPUs. Very nice scaling. If you go all the way to 64 GPUs, that's where the 1-bit technique really doesn't work that well anymore. But with the block momentum technique, you can scale all the way up to 54. So you get very, very nice speedups out of this. And these techniques typically don't cost you any accuracy, or if sometimes a tiny bit, like 0.1 on the error rate. You can see this at the bottom, 11.08. And turns out in this case, actually, it got a little bit better, so there's also some noise involved. But this actually works very, very, very nicely. And again, if you want to invoke that, just put MPI exec in front, and there you go. And you have to say which method you actually want to use. OK, so I would like to go through a couple of examples. So the first example I want to do is a convolutional network. So I don't really have time to explain a convolutional network. If you are not familiar with that, maybe wait to the next example. So this example is very simple. You start with a convolution, put a max pooling on top, do another convolution. In both cases, you have a rectified linear unit at the end, another max pooling, another convolution, another max pooling, and now you put a dense layer, a fully connected layer, and another one where you actually don't take the softmax at the end because we normally move this into our training criterion. So let's write this in BrainScript. It's this. Right? So it's a very direct representation of what your model looks like. And I want to show you what the complete file for this looks like. This is the actual config file that I could run right now. So you see there's a couple of definitions in the beginning, and this is your block here. It's called train.confnet. You see there's the action, the network builder, which has the block that I just described to you here, and then a bit of boilerplate. You have seen this before. You declare what your inputs are. You apply your model. You connect it to your training criterion, and that's it. You tell the system what the nodes are. You also need to define SGD and the reader. The reader is a bit more complicated, but this is, I think, the example I used earlier on. Okay, and this is literally all you need to specify, and now you can run the system. So another example I want to show you is language understanding. So language understanding, in this case, I want to use the slot tagging task. So you see what it does. It takes an input, show flights from Burbank to St. Louis on Monday, and it tries to classify every single word into what slot it fills. So for example, Burbank is a from location, and St. Louis is a to location, and Monday is the departure date. So the task is to make this kind of annotation. The left column is your input, the right column is your target. So the first thing you need to do is, in this case, you would want to convert that into sort of the CNTK native text format. We have a tool for that, a Python script. And then you get something like this. You don't really need to understand in detail right now what it means, but maybe I can explain that these numbers here, these are column indices. And 178:1 means this is a sparse representation that has a 1 at the particular row 171. And the next thing you need to do is you need to define what your model structure is. And I'm going to use a very simple model structure here that starts with an embedding layer, then a recurrent network, and a dense layer for classification. And this is a recurrence, so let me just show you how this works. Well, you start with your first word, beginning of sentence. You run it through here, and the target is nothing here. Then you execute the recurrence. So you add the next word, also run it through the same embedding. The LSTM now takes the previous state of that recurrence also into account, and this way you can classify the next one, and so on, and so on. So this is the model that we're implementing in. But really, we think on this level here, right? So this is how you write it in CNTK. So the numbers there are basically the dimensions that I have chosen, 150 dimensional embedding, 300 for the recurrent hidden state, and label dim is the number of output labels. So it's a very direct representation of what your model actually looks like. And just for the fun of it, I'm just going to run this just to prove that this thing actually runs. So this is how you would run it. You see here CNTK. I passed the corresponding config file. This is actually available online. We have a hands-on tutorial for this and also for the previous example that I showed. And you can find a full explanation of everything there. And now it's running. First epoch here, it has an error of 15%, I'm sorry. And now it goes down to 5 and so on. So we can let this run now if we want. And the last example I would like to give is what that would look like in Python. Now, this is not yet available in the current version, but as I said, this is scheduled as a beta version for October. So I'm going to use exactly the same model. And in Python, turns out it really looks very much the same. Right? You have, again, the embedding layer. Sorry for this kind of complicated name. That will simplify. And it's exactly the representation of the network there. Now, if you want to run that, you have to do the same things. You need to declare your inputs. You need to apply your model. You need to define your criteria, your training criteria and a metric. And you need to create the reader. And then you can run it. So in this case, for example, you create a trainer object, and you can get and feed the mini batches one by one. This is one of the things that the Python API will give you, that you can now control the mini batches you're passing to it. Whereas the command line version that we have at the moment just runs a very strict SGD algorithm. And you can see what it does. Well, it just passes in the data here, calls train mini batch, and counts the mini batches, maybe prints some training progress. So it's very straightforward. And actually, there's going to be a convenience method that does this for you. It's going to be a one-liner if you don't care to actually pass data in. OK, so let's see how this other guy is doing here. OK, so this one has finished. In this case, I ran 8 epochs. So the training error rate got down to 1.4%. And the test error rate is 2.9. So that's for this very simple model that we're training, actually not bad on this task. OK, so I got 55 seconds left. That's great. So I'm going to go to the conclusion. Oh, let me first talk about what we plan, what's on our roadmap. The most important next thing that we'll put in is the C++ and Python API. So what does this give you compared to what we have right now? Well, it gives you IDE support, IntelliSense. It gives you the ability to reuse data I/O code that probably many of you already have lying around in Python, and you can make direct use of that. And it allows you to implement SGD-like algorithms that do not follow the rigid pattern. For example, reinforcement learning, where you need to sometimes generate new data in between as you're going, or adversarial learning, where you're reading from multiple sources of different formats in different sort of schedules. We're working on integration with, well, the next stage will be integration with .NET and C#. At the moment, we have an evaluation library, but not the full API. And R is a very popular request at the moment. A lot of people also ask for Keras integration, so we're seriously looking into Keras backend. And on the I/O side with HDFS and Spark. On the technology side, we're going to look at the problem that models no longer fit in memory sometimes, the GPU memory. So we will look at memory swapping and model parallelism. There will be refined models like deeper nested loops, CTC. On the training side, we're planning to support ASGD, and NVIDIA was so kind to contribute a communication layer for the DGX-1 that makes the data communication more efficient there. And on the evaluation side, we're looking at 16-bit support, ARM support, but also on the other end, that will eventually run on the FPGAs in Azure. Okay, so let me summarize. So CNTK, democratizing the AI toolchain. It's easy to use, right? You focus on what, not how, in terms of it gets off your mind, the sequence batching, unrolling, padding business, gradient computation, memory use, reuse, parallelization. And then has this powerful stock library for feed-forward DNNs, recurrence, convolution, and so on. It's fast. It's optimized to be running very well on GPUs. And I think it has the best-in-class multi-GPU and multi-server support across all the toolkits. It's very flexible, right? It has this down-to-earth, elegant, I think, powerful, composable network description language called BrainScript. But if you kind of feel you don't like that, you can go to Python very soon. And again, it is a first-class citizen on Windows, not only on Linux. And the internal version is equal to the external version. You are up to date with what the Microsoft product groups also use. So where do you go from here? If you're interested, please check out cntk.ai. And from there, you will also find the links to GitHub, to the source code, to the wiki. And if you have any question, you can go to the issues forum, for example, and ask a question there. Feel also free to just send me an email. And I will also be available at this Meet the Speakers event, which is starting, I believe, right after this at 1:30 in the convention center at room A408. That concludes the talk. Thank you very much. And we have time for questions. Yes. I think if you could step to on the microphone, then it will be recorded. Oh, no microphone. Or you can also, I can repeat your question. Why don't you just ask it? I'm sorry about that. Yep.
But there is no way to define your topology as part of the batch.
Mm-hmm. Yep. So the question was whether it is possible to define the topology with respect to the batch. So specifically, sorry for it. Per single run. Oh yes, that's what you're doing. But you're basically describing it in terms of the formula for a single sample and the single sample as part of a time sequence through the past value operation. But you're very flexible. I mean, you saw the whole chain, right? You can go all the way to the most simple linear layer definition that you can write yourself, or you can use these prepackaged. Mm-hmm. Oh yeah, you can do this. You can use this. Yeah. The past values, then you will probably no longer be able to utilize the prepackaged modules, but you can still then step one layer down, which is kind of an interesting thing here because, for example, if you work in Keras, right, the moment you are going beyond the limitation of Keras, you have to step down into a completely different world, right? In this case, into TensorFlow or Theano. In CNTK, that's not the case. It's all in the same world. It's just different abstraction layers. And all these layers are actually implemented in BrainScript. Just the way, as the example was written that I gave you there. And the real ones are just a little bit more complicated. If they don't do exactly what you want, you can actually copy it. It's also open source, and you can modify it and create your own. Yeah. There was another question on this side. Okay, any more question? Over here, okay.
Would you mind please going to the mic, just so we get the question on recording? Thank you.
Yeah. So the question was about FPGA support, right? What? Oh, CPU. So everything runs on this, nearly everything runs on the CPU. There's one particular operation that at the moment will not, that's batch normalization. For some reason, batch normalization we have not ported yet. That's going to be there very soon. Multi-mode CPU is the same as GPU. So it's happening on 2 levels. So multi-node is just MPI. And since CNTK implements pretty much everything on the CPU as well, we have a mirror of all the functions. It will run multi-node CPU as well. However, I would not really recommend that. Okay, the thing that you have going for you is that the computation itself is much slower. It's really much slower. It's 10 times slower or something like that, right? Which technically means you can parallelize 10 times better, approximately, right? So if you use 10 times as many machines, it's typically not how we run things. The moment you parallelize over too many machines, you're no longer on the same switch, so you get all this additional overhead and so on. So our strong recommendation is go for GPUs. And you may know that Azure has already released GPU servers that you can rent. At the moment, there is some sort of limited phase where you have a maximum number of GPUs you can get. I think it's only 1 GPU at the moment, but that will come soon. And you can actually run also parallel jobs over multiple such servers through HPC in that farm. Any more questions? Yeah.
Can you use knowledge transfer to transfer previous training of some layers to a completely new network?
Yes, you can. There is a mechanism called function cloning. So I don't have a slide for that, but imagine you are, you're looking at that graph that I drew, right? What you can do is you can basically like circle a section of that graph and say, take that and cut it out and package that into a function that I can then use in a different network. And you can do it in 2 ways. 3 ways. One is read-only. So then in this way, you could, for example, use a pre-trained image recognition model as a feature extractor and then apply that, say, to a smaller data set. Or you can keep training it. That sometimes you have these techniques where you keep building and adding layers, but then retrain it. It can also perform adaptation in that way. And so you can, for example, use KL divergence regularized adaptation, where you switch to a smaller specialized data set, but you keep the model close to the original model as a regularization term. You can directly express that in BrainScript in this way. And the third thing you can do is you can also share parameters. So you can instantiate a clone of a network multiple times, but the underlying parameters just remain the same. That's also useful in some situations.
I couldn't find in the examples, maybe I didn't look hard enough, but is there a way to configure the SGD to terminate training when the error rate gets below a acceptable threshold?
At the moment, we have something that it terminates when it doesn't get better. So basically, it keeps track of how the cross-validation criterion, which can be the error rate, how it improves. And if it doesn't improve, then it will cut the learning rate. And if it has basically cut it to a point where it sees it doesn't get better, then it will stop. But at any point in the training, you can always just cancel it. And what CNTK does is it does checkpointing. So after every epoch, it will freeze the current state, so you can restart. And that checkpoint model is just a model, you can use that. And this actually is what we do quite often, is that we let the full training run, and then we actually use a different test set, another development set or tuning set, and evaluate all, a range of those models one more time and pick the one that's the best.
Oh, thank you.
Can you speak to success or challenges in getting to have the different teams across Microsoft use this tool set?
Oh, that's a very interesting question. Well, I think the most important challenge is to gain the trust of the product groups, right? So it's not, Microsoft is such a big company, it's 100,000 people, and it's not a dictatorship. So even if Satya really likes CNTK and he goes to Bing and says, you all have to use Bing, okay, yeah, well, we'll look at it. So the way to actually get people to use it is to, well, go out, do what I do today, give talks. We actually have a team, an entire team that helps product groups to set up tasks and also learn from what the challenges are that they're facing, and then help us implement things or fix things that are necessary. And so all of these things work together. Any more questions? Yeah. One more.
My question is about how to put this in production. I mean, we train the model and we want to put it for a live example.
Yeah, so there's two ways. One is that although CNTK itself is a command line tool, the algorithms have been packaged up in this library. It's called eval.dll. And that's the current state. So you can, it's just something you can call from C++ and from .NET in this case. We already have a .NET wrapper for that. And you can use that. And this is how, for example, Bing users are serving their data out of that. Once the, I mean, Bing internal users, the product groups that develop Bing. Once the C++ API has been completed, then everything will be, it's not only the evaluation that's accessible, it's everything will be accessible in the example that I showed you. I only showed you a training example, but the evaluation will look very much the same. You have the same data structures, and each of the networks have a forward method. You can pass data in the same way that the trainer passed the data in the Python example, and then at the end get the result out.
Okay, but
and
for production with scalability, like for example, it's done with Spark and TensorFlow, so do we have something in this way?
Right, right. Yes, I mean, it's just a C++ library, right? There are a couple of special things that you want to do. So for example, you want to disable parallelization. We're using OpenMP. If you do this, if you run a single job on a 32-core CPU, then you want to have automatic parallelization. But if you're controlling the inference process yourself or the threading yourself, you want to reduce that to 1. So there are options for doing something like that.
Okay. Thank you.
Any more questions? Okay, so if you have any further questions, please, you can come over to A408 and have more detailed discussions. Thank you very much.